Hello and welcome to my academy once again. Now let us read the question. Which of the following is not a standard transmission voltage in India? Option A 220 kilovolt, option B 99 kilovolt, option C 66 kilovolt, and option D 33 kilovolt. Now before selecting the option, let us know the concept first. We know that power system is divided into three stages, namely such as generation, transmission and distribution. So let us know the voltage level of each stage in detail. Usually we use 11 kilovolt for generation purpose, whereas 220 kilovolt, 400 kilovolt and 765 kilovolt are extra high voltages. We employ them for primary transmission because when we use high voltages for transmission, they allow us to use thinner wires, resulting into saving in conductor materials. Moreover, use of high voltages for transmission purpose reduces current, which further minimizes energy loss. As the power gets closer to the city, we step it down for safety. Then 66 kilovolt, 110 kilovolt and 132 kilovolt are high voltages we use for secondary transmission. Secondary transmission generally connects the main grid to regional or city substation. Then 11 kilovolt or 33 kilovolt are medium voltages we use for primary distribution. Primary distribution usually bring in power from a larger substation to our local area. Finally, 450 volt 3 phase or 230 volt single phase are low voltages we use for secondary distribution. Secondary distribution takes the 11 kilovolt or 33 kilovolt power from the primary distribution lines and step it down to a level that is safe voltages used in households and small shops. Therefore, from the discussion, we can conclude that 220 kilovolt, 66 kilovolt and 33 kilovolt are the voltages we use for transmission of electrical power, but we never use 99 kilovolt in practice to transmit electric power. Therefore, option B is the right choice. Now let us move on to the next question. A load power factor of 0.95 lagging implies reactive power demand of option A 0.05 kilovolt ampere reactive per kilowatt, option B 0.95 kilovolt ampere reactive per kilowatt, option C 0.10 kilovolt ampere reactive per kilowatt, and option D 0.33 kilovolt ampere reactive per kilowatt. Now, in this question, we are asked to find the reactive power demand per kilowatt for a load with a power factor of 0.95 lagging. Question mention load is lagging. It means it is an inductive load which consumes reactive power. Now let us break down the relationship using the power triangle. You can see the power triangle on the screen where P represents active power measured in kilowatts, Q represents reactive power measured in kilovolt ampere reactive, and S represents complex power measured in kilovolt ampere. Now, complex power can be represented in terms of active and reactive power like this P plus JQ. Since cos phi is equal to 0.95 lagging given in the question, first we find the angle by taking the inverse cosine of 0.95, which gives us approximately 18.19 degrees. Remember, the power factor is simply the cosine of the phase angle. To find the ratio of kilovolt ampere reactive per kilowatt, we actually need the tangent of that same angle. Therefore, tan of 18.90 is equal to 0.328. Rounding our result to 2 decimal places, we get 0.33. Now from the power triangle, we can express tan phi in terms of active and reactive power. Tan phi is equal to Q by P, perpendicular divided by base. Then solving it for Q, we have equation like this: Q is equal to P tan phi. Now put all those values in the Q is equal to P tan phi. Now assume P is equal to 1 kilowatt. Therefore, Q is equal to 1 into 0.33 kilovolt ampere reactive. Therefore, Q is equal to 0.33 kilovolt ampere reactive per kilowatt. Looking at our options, the correct choice is option D. Third question, if supply frequency increases, the skin effect is option A decrease, option B remain same, option C increase, and option D none of these. Now we know that skin effect is nothing but the tendency of an AC current to concentrate near the surface of the conductor. From the famous formula skin depth, we can say skin depth is inversely proportional to the square root of frequency. A higher frequency means smaller depth. A smaller depth means more pronounced skin effect. The key thing to remember is that the skin effect is directly proportional to frequency. As the supply frequency increases, the magnetic field inside the wire forces the current further toward the surface due to increase in magnetic resistance or magnetic reactance, leaving the center of the conductor with almost no current flow. So we can say that if the supply frequency increases, the skin effect is increased. This is why high frequency applications often use hollow conductors or stranded wires to reduce resistance. Now, from the discussion, we can conclude that if supply frequency increases, skin depth decreases, which increases the skin effect. Therefore, option C is the right option. The material commonly used for sheaths of underground cable is option A, copper, option B, rubber, option C, steel, option D, lead. In this question, we are looking at the construction of underground cables. Specifically, we need to identify which material is used for the metallic sheath. Now, you can see the construction details of cable here. Before knowing which option is correct, let us know the significance of each material in detail. Copper is generally used as a conductor material. Now steel is used in the armoring layer for mechanical strength. Now let us know the significance of sheath. The main purpose of the sheath is to protect the insulation from moisture, gases, and other damaging liquids in the soil. If moisture enters the insulation, it can lead to a complete breakdown of the cable. Therefore, we need to choose material for sheath very carefully that should possess the properties like corrosion resistance, flexibility, and waterproofing. Now, from the given options, there is only one such material, that is lead, which is commonly used because it is highly resistant to corrosion and completely waterproof. It is also flexible enough to allow the cable to bend during installation without cracking. Hence, lead remains the standard choice for the protective moisture-proof sheath. So, the common material used for the sheath of underground cable is lead. The correct option is D. The permissible variation of frequency in power system is option A plus minus 10%, option B plus minus 5%, option C plus minus 3%, and option D plus minus 1%. Now, let us know the significance of stable frequency, since operation of AC motors depends on frequency for their speed. If the frequency drops too low, motor slows down and can overheat. If it goes too high, they can overspeed and cause mechanical failure. Therefore, according to IE rules 1956, the permissible variation for frequency is plus minus 3%. This tight margin ensures that all connected machines and generators stay in synchronism. Therefore, upper limit of frequency is 50 plus 3% is equal to 51.5 Hz. Now, lower limit is 50 minus 3%, that is 48.5 Hz. So, the given choice here is plus minus 3% is the correct option. The permissible variation of frequency in power system is plus minus 3%. To meet the reactive power requirement at load centers, usually option A, tap changing transformers are used, option B, shunt reactors are used, option C, shunt capacitors are used, and option D, series capacitors are used. Now we know that most industrials and residential loads at the load center are inductive in nature, that is, they absorb reactive power. Think of motor, fans, and transformers. The load consumes reactive power, which leads to lagging power factor and voltage drops. Therefore, we have to install equipment at the load center so that they should supply leading reactive power. To meet this demand locally, we use shunt capacitors. Think of shunt capacitor act as a local generator of reactive power. By installing them in parallel with the load, they supply the reading bars that the inductive load requires. In simple terms, Inductive loads need volt-ampere reactives and shunt capacitor provide them. That is why option C is the standard practice. Now let us see each option one by one. Tap changing transformers. Tap changing transformers mainly used for voltage regulation, not for supplying reactive power. Option B, shunt reactors. Shunt reactors consume excess reactive power on long, lightly loaded lines to prevent overvoltage. Now option C, shunt capacitors. Shunt capacitors, now we have discussed, supply the leading wires and act as a source of reactive power. And option D, series capacitors. Series capacitors used to reduce line impedance on long transmission lines to improve stability. Therefore, from the discussion, we conclude that option C is the right answer. To meet the reactive power requirement at load centers, usually shunt capacitors are used. The ratio of puncture voltage to the flashover voltage of an insulator is option A 0, option B greater than 1, option C equal to 1, and option D lower than 1. Now, to answer this question, let us know what is the difference between puncture voltage and flashover voltage. Now, you can see in the image an insulator holding up a high voltage power line. If the voltage increases beyond a predetermined value, resulting into electrical arc develops. As you can see in the image, electrical arc gets developed when voltage increases beyond the predetermined value. And this arc jumps through the air, traveling around the surface of the insulator to reach the grounded tower. This is called as flashover, and the voltage at which this happens is called as flashover voltage. However, flashover causes a temporary short circuit, but the physical body of the insulator remains intact. Now let us consider what is puncture voltage. Now you can see in the image once again, puncture voltage is nothing but the voltage level where electrical stresses become so intense that current directly passes through the solid body of the insulator. Now you can see current directly passes through the body of the insulator. Unlike a flashover, a puncture voltage completely and permanently destroys the insulator. That means once insulator comes in contact with puncture voltage, it has to be entirely replaced. From the discussion, we conclude that magnitude of puncture voltage is greater than magnitude of flashover voltage. Now, when we divide higher value by lower value, the resultant will be greater than 1. So, the ratio of puncture voltage to the flashover voltage will be greater than 1. Therefore, we can say option B is right. The ratio of the puncture voltage to the flashover voltage of an insulator is greater than 1. Now, let us move on to the next question. Advantages of transmitting power at high voltages. Option A, it will reduce the voltage drop in the line impedance. Option B, magnitude of current will be small. Option C, loss will be less. And option D, all of the above. Now, to understand the concept of this question, let us consider the famous equation of three-phase power, which is equal to √3 VL cos phi. Now, on arranging this equation in terms of line current, we have equation like this. IL is equal to power divided by √3 VL cos phi. Now, from the equation, we can observe that line current is inversely proportional to magnitude of voltage. When we increase voltage, the magnitude of current will get reduced. Therefore, on transmitting power at high voltages, magnitude of current will get reduced. Therefore, option B is the correct. Now, due to reduction in line current, voltage drop in the line impedance will also be reduced. Therefore, option A will again be correct. Now, due to decrease voltage drop in the line impedance, voltage profile improves. That means we have better voltage stability. Now, let us validate third option. We know that power is directly proportional to square of current. As the magnitude of current get reduced, power loss in the line will reduce. Therefore, when we transmit power at high voltage, magnitude of current will be reduced. Therefore, losses in the line drastically reduce. Thus, we can say transmitting power at high voltages reduces voltage drop in the line impedance. Therefore, voltage profile improves. Magnitude of current will be small. Therefore, power loss is reduced. Hence, option D is the right choice. Voltage drop is the main consideration while designing a distributor, option B service mains, option C feeder, and option D all of the above. You can see the image. This is a transformer located at the substation which supplies power to the distribution transformer by means of feeder conductor. Distribution delivers power to the residential and commercial areas by means of distributor and service mains. Now let us validate each option one by one. A feeder connects the substation to the distribution area without any intermediate tappings. This means the current remains constant along the entire length of the feeder. Now you can see there is no any intermediate tappings. Since there are no consumers connected directly to feeders, therefore feeders are designed based on their current carrying capacity and thermal limits to prevent overheating. On the other hand, distributor is the conductor from which numerous intermediate tappings are taken out to supply individual consumers. Now you can see in the image, this is distributor. This area indicates distributor, and there are various tappings taken out to supply individual consumers. Because current is driven at various points along its length, the current density varies throughout the line. Hence, the most critical requirement for a distributor is to ensure that terminal voltage must be constant. Therefore, distributors are designed on the point of view of voltage drop. Finally, service mains are the cables. Now you can see the image. There are 3 cables, 1, 2, 3. These are called as service mains. Therefore, it must be designed first to provide a stable voltage base for these connections. Thus, we can conclude that because the distributor must maintain steady voltage for all connected consumers despite varying loads, voltage drop is the main consideration. Therefore, the correct answer is option A. Distribution transformers are designed to have maximum efficiency nearly at option A 10% of full load, option B 25% of full load, option C 50% of full load, and option D 100% of full load. Now we know that efficiency is a critical parameter for any electrical machines. However, the point at which transformer reaches its maximum performance depends upon its application where transformer is used. Now you can see in the image, distribution transformers are connected to consumer whose demand fluctuates throughout the day. While they are energized 24 hours a day, incurring constant iron losses, they are only heavily loaded during peak hours, such as evening. For maximum times of the day and night, they operate at a light load. Therefore, we can say the average load on a distribution transformers over a 24-hour period is typically between 40% to 70%. Hence, we design them to reach peak efficiency at approximately 50% of their full load. This ensures the highest all-day efficiency. Now, distribution transformers attain its maximum efficiency at 50% of full load, and they are designed with low iron losses. Now, as far as power transformer is concerned, they attain their maximum efficiency at 90 to 100% of full load, and they should be designed for low copper losses. Therefore, from the discussion, we can conclude that option C is the right choice. Distribution transformers are designed to have maximum efficiency at 50% of full load or nearly 50% of full load.